So let's take a look at question 1. Now this question wants us to find the coefficient of x to the fifth from this product of two polynomials here. Now rather than expanding the whole thing out, the best thing we can do is take a look at which term from the bracket on the left combined with some terms from the bracket on the right will be able to give us x to the fifth. So we notice the left bracket has this 4 on the outside, so this means the highest power of x it can generate is x to the fourth. So therefore, if we look at the terms on the left times the term on the right, x to the fourth times x to the 1 will give us an x to the fifth. But then we have more than that. And now we really just run through until we run out of terms on the left. Now all we have to do is expand the x to the fourth term on the left, the x cubed term on the left, and so on, and the x to the 1 and the x to the fifth term on the left, and multiply these together and then add them all up. So with the first term, for example, if we take a look at the x to the fourth coefficient from the left and the x to the 1 coefficient from the right, the x to the fourth coefficient on the left is just this, and the x to the 1 coefficient on the right is just this. And then similarly, we want to look for the x cubed coefficient on the left, which is just this term, times the x squared coefficient on the right, which is just this term. And now, if we fill in all the others, which is quite straightforward to do, we can now plug all of this into our calculator using the useful fact that if you have -1 to an odd power, that just gives you -1, and if you have -1 to an even power, that gives you +1. We can plug all this in, and we do find the answer is -12, which means our correct answer is A. On to question 2, we have to just find the value of x in this expression given. So this second term here, the log base 4 of 16, we can quite simply write down as 2, just based on what we know about logarithms and how they are the inversion of something raised to some power. So this is an equivalent statement to 4 squared is equal to 16. So we have log base 2 of x plus 2 is equal to 2. Of course, that rearranges to log base 2 of x is equal to 0. And now inverting this expression using our knowledge of logarithms, this is equivalent to saying 2 to the power of 0 is equal to x. Therefore, x is 1 and B is our answer. And question 3, now this is one of those topics I mentioned that is not a year 12 topic, that is something you will only study in year 13 if you're at a high school in the UK. So the product rule and the chain rule, make sure those are things that you're comfortable with and you've talked to your teacher about, and you're happy doing questions like this when you come to sit the pad. So if we just label x sine of x squared as f of x, f prime of x, following the standard sort of prescription of the product rule and the chain rule, we'll have first, we'll take the derivative of this first term, which is just 1, times the second term not differentiated, and next we have to add that to the first term times the derivative of the second term. And the derivative of the second term requires us to use the chain rule now. So in finding the derivative of sine x squared, what we first do is we differentiate the inside of the bracket, and that gives us a 2x, and then we differentiate the outside of the bracket with respect to what is on the inside. So we treat the x squared as if it was just an x, and that gives us cosine of what is inside, which is x squared. So that gives us sine of x squared plus 2x squared cosine of x squared, which is answer D. Question 4 now wants us to find the gradient of the line joining these 2 points. So this is quite a simple use of our gradient formula, where m being the gradient of the straight line is the change in y over the change in x. So in order to do that, we just have to plug in one y value minus another y value. So let's say 8 minus -2 over the corresponding x value minus the other corresponding x value. So that gives us 4 minus 5, which when we work out gives us 10 over minus 1, which is minus 10. So the answer is A. Now on to question 5. We are looking to sum all of the integers between 1 and 100, a problem that is sometimes attributed to a very young Gauss given to him by a maths teacher that thought he was a bit obnoxious. So when we do this, we could quite easily use the formula for summing an arithmetic progression, where n is the term we want to sum up to in the series, d is the common difference between neighbouring terms, and a is the value of the first term. But actually, for this very simple example, I think it's quite easy just to do the number of terms, that is 100, times the average value of each term, which is the value of the first term, plus the value of the last term, and then all divided by 2 to account for the double count we've done in adding the first and last terms together, and so on. That gives us this, which is 5,050. So the correct answer is C. Now, question 6 is the hardest question we've seen so far, and is basically a question of combinatorics. So we want to find how many numbers greater than 5,000 can we form from the 5 digits 3, 4, 5, 6, and 7. So there are two kinds of number we can form from these 5 digits. Obviously, we can form a 5-digit number, and we can form a 4-digit number that we'll look at after. So for the 5-digit number that we can say has digits n1, n2, n3, n4, and n5, there's really no restriction on which of the numbers 3, 4, 5, 6, and 7 we can assign to these, because whatever number we put for n1, this is a 5-digit number, it's in the 10,000s, so it doesn't matter if it's 30,000, it's still bigger than 5,000, which won't be the case for the 4-digit number. So for n1, we have 5 choices. We can choose 3, 4, 5, 6, or 7. Then for n2, crucially, we're not allowed to repeat numbers. So now, after we've used up one choice for n1, we only have 4 choices. For n3, similarly, we now have 3. n4, we have 2. And n5, we have 1. So the total number of choices for a 5-digit number is given by the product of these, which is 120. And now a 4-digit number. Now this is a little bit more tricky because now we're no longer allowed to put just any number as our first digit. So if we call our 4-digit number M1, M2, M3, M4, for this case, now M1 can only be 5, 6, or 7. So it has 3 choices as to what we can call it. Then M2 after that. Now M2 can be any of the above numbers. It can be 3, 4, 5, 6, or 7. But as we've already used up 1 in choosing M1, we are now down to 4 choices, just as we were for N2 above. And then the same sort of thing follows. So M3, we have 3 choices, and M4, we have 2 choices. And now the total number of choices from this will be 3 times 4 times 3 times 2, which is 72. So the total number of choices from the 4-digit number and the 5-digit number is 120 plus 72, which is 192, which gives us answer C. So this question now gives us a list of 5 claims about the properties of planets in our solar system as we move away from the Sun. So we're going to go through this in order. First, we'll take a look at question 1. Claim 1, sorry. The duration of the day on each planet increases. So this isn't something realistically we can expect to be true. The duration of a day on a planet is to do with how quickly it's rotating about its own axis, which isn't reasonably something that will depend on the radius from the Sun. And also, if you just happen to know this, a day on Jupiter is something like 9 hours, so that is a clear breaker of that trend. Claim 2, the duration of the year on each planet increases. Now this is certainly true. This is due to something called Kepler's third law that says the orbital period squared of something in orbit is proportional to its orbital radius cubed. That's for a circular orbit, but it is actually true for elliptical orbits, just rather than the orbital radius cubed, it's something called the semi-major axis of the elliptical orbit. Claim 3, the size/volume of the planet increases. Now there's one I can think of that certainly bucks that trend, and that is Earth and Mars. Mars is much smaller than Earth, so that is not true. Claim 4, the number of moons on each planet increases. Again, the counterexample to this would be Saturn. So Saturn has the most moons of any planet in our solar system, and then of course after Saturn you've got Uranus and Neptune. So they would of course have fewer moons, so that is not true. Claim 5, the planets change from rocky to gas giants. So this one is true. The inner planets like Mercury, Venus, Earth and Mars are all rocky, and then the outer planets, Jupiter, Saturn, Uranus and Neptune, are all gaseous, or Neptune and Uranus are also sometimes called ice giants because they do have some very dense astrophysical ices, but they are still mostly gaseous. So claim 5 is certainly true. Therefore, I am saying that D is the correct answer. Question 8 is just one of those sort of annoying ones you kind of just have to know. It's useful to be familiar with the different parts of the electromagnetic spectrum, knowing which wavelengths fit into which band. So this question gives us a frequency rather than a wavelength. And personally, I try and remember these things in terms of wavelengths. So the first thing I'm going to want to do is to convert this into a wavelength using the wave equation. So we put in the speed of light, and then 100 gigahertz is 10 to the 11 hertz. That gives us 3 times 10 to the minus 3 meters, which is 3 millimeters. And now again, one of the just silly things you have to remember for this exam, and but is, I suppose, good for your general physics knowledge as well, is that wavelengths between 1 millimeter and 1 meter fit in to the microwave band. Therefore, this 3 millimeters certainly fits into that. So I say the answer is C, microwaves. This question again gives us a number of different scenarios we have to evaluate which will be true. So we have an object that is attached to the ISS, the International Space Station, and it becomes disconnected while the ISS is in orbit, and we have to think what will happen to it. So they say A, it'll follow the ISS in its orbit. B, it'll go straight along a direction tangential to the ISS's motion. C, it'll fall straight down towards Earth. D, it will stay still with respect to Earth. Or E, it will orbit the ISS. So if we know Kepler's third law, again, this is quite straightforward. So Kepler's third law is the orbital period squared is proportional to the orbital radius cubed. And if we write that out as a proportionality relationship, where K is this constant of proportionality, if you know Kepler's third law, you know that this K only depends on the mass of the thing being orbited. So in this case, this is the mass of the Earth, and does not depend on the mass of the things in the orbit. Therefore, if this small object was in the same orbit as the ISS beforehand, it'll stay in that orbit. because there's no dependence on the smaller object's mass. So we can think then also about E. Could E possibly be true? But in fact, no, I don't think it could, because the masses of the ISS and the mass of this object, although we don't know the mass of this object, are so small that you couldn't possibly form an orbit between the two of them at that closer distance. So the correct answer is going to be A. An alternate way we could think about this, if we don't know Kepler's third law, is just to think about the forces involved. So the only force that's involved is gravity, and we know that the gravitational force is proportional to the mass of the Earth times the mass of the object that is in orbit over the radius squared. Now, if we want to find an equation of motion for something moving in the gravitational field around the Earth, we know that we're just going to have to use F equals ma, where m is the mass of the object that we're finding the equation of motion for. So we can see that when we equate these in F equals ma, that we will always be able to cancel the mass of the object. So whatever equation of motion we derive, where the only force is gravity, it will not depend on the mass of the object itself. So therefore, we can kind of make the same conclusion we drew from Kepler's third law, that the kind of orbit we have doesn't depend on the mass of the object in the orbit. Therefore, if it was in an orbit the same as the ISS, just because it now is not attached and has a smaller mass, doesn't mean that that orbit will change. Lo and behold, we have another Kepler's third law question. This question tells us that there are two satellites in an orbit around the Earth. One is in a geostationary orbit, meaning it stays fixed above a certain position on the Earth's equator, and the second is at a radius half of the first. So we need to find the period in hours of the second one, that is at the half distance radius. So first of all, what is the period of the first one? The period of the first one is just 24 hours, as it orbits with the Earth. And now we have Kepler's third law again. The orbital period squared is proportional to the orbital radius cubed. And if we write that out as an equation rather than as a proportionality relation, we have this. And the crucial thing, again, we need to remember is that k only depends on the mass of the thing that is being orbited, in this case the Earth. It does not depend on the mass of the satellites or the radius of the satellites or anything like that. It is just a constant that depends on the mass of the Earth. Or if we were talking about planets going around the sun, it would depend on the mass of the sun. So if we call, we'll call the first satellite T1 for its 24-hour orbit. So now we have T1 squared is equal to k radius 1 squared, and T2 squared is equal to k, where these k's are the same, radius 2 squared. Now we can divide these two equations by each other and cancel the k's. Also, sorry, those should be cubes, not squares, of course. So now if we plug that in, we know that R2 is half of R1, because we're told the second satellite is at a radius half that of the first. Therefore, this whole side here is equal to 1/8, 1/2 cubed. And that means T2 is equal to T1 over 8, all square rooted. Sorry, T1 squared over 8 all square rooted. And if we put that in with 24 hours, we end up at 8.48 hours for T2. Now in question 11, we're looking at radioactive decay. We're told that A has a half-life of 3 days and B has a half-life of twice the length at 6 days. And then we're told that initially we have twice as much A as we do B, and we want to find the time that that ratio is reversed. So when we have twice as much B as we do A. So the main thing we're going to be using in this question is the radioactive decay law, which you can write like this, where lambda is called the decay constant and takes the value natural log of 2 over the half-life. But I actually don't like writing it in this way. I prefer if you just sub in what the decay constant is, you can see that we also have the number of undecayed particles at n2 is given by n0 times 2 to the minus t over the half-life. So now we just write down these two expressions for A and B using their separate half-lives in days. Where A0 and B0 are the values they have at the start when t is 0. Now we want to find at the time that bt over at is equal to 2. So using those two expressions we have, this tells us that we are looking for when b0 over a0 times 2 to the minus t over 6 plus t over 3 is equal to 2. Now we know that b0 over a0, that is right at the beginning, is equal to a half, because we have twice as much a0 as we do b0, and we can simplify this exponential as just t, 2 to the t over 6. So if we put all that together, we get 2 to the t over 6 is equal to 4, moving this half to the right-hand side. And that, of course, tells us that t over 6 is equal to 2, which implies t is equal to 12. So the correct answer is D. For the last of these multiple choice questions, we're told that we start off with a cube that is painted black on the outside, and we cut it into 125 identical cubes. And we want to find how many of these cubes are not at all painted. So let's start with our cube. Now, if we're cutting a cube into 125 identical smaller cubes, that means the length of the cuts we have to make in the original cube are the cube root of 125, which is 5. Therefore, we're cutting this cube into 5 slices along every direction. It's going to get quite nasty at the top. My drawing is really not the best. Okay. So all of the cubes that won't have any paint on will be the ones not in this kind of external top layer. So what we have to do, what is easiest to do, is to count all of the cubes that will be on this top layer. So there are kind of 3 different kinds of cubes per face. There are these red ones I've drawn that are only counted once. They only appear each on one face. So we can take 9 of these and multiply by the number of faces. But then there's another type of cube that appears at the intersection of 2 faces. These are these 12 all around the edges. So for these cubes, we have 12 lots of 6, but because they appear on a shared edge between 2 faces, we have to divide by 2 to get rid of the double count. And then lastly, we have these corner cubes, and these appear sharing 3 faces. And there are 4 of these per face, so we have 4 times 6, 6 being the number of faces, but to get rid of the triple count, we now have to divide by 3. And if we follow all that through, we get 98. And now, to find the total number that aren't painted, what we've got 98 here is the total number that have any amount of paint on. We have to take 125, the total number of cubes, and subtract the painted ones, and we find that there are 27 completely unpainted cubes, which is answer D.